In this class, we'll discuss about action potential in neurons. This action potential will help in transfer of information from one neuron to other neuron. All the cells will have a potential called as resting membrane potential. That means whenever the nerve fibers, when they are not transmitting signals, then they will have a potential inside them, and that potential is called as resting membrane potential, and this resting membrane potential is around minus 90 millivolts. And this resting membrane potential is contributed by three factors. One is contribution of the potassium diffusion, which produces a potential. Next one is contribution of sodium diffusion through the nerve membrane, and next one is sodium potassium pump. These are the three factors which help in maintaining the resting membrane potential, RMP. And first we'll discuss about contribution of potassium diffusion potential. In the membrane, we have potassium leak channels. Through these potassium leak channels, the potassium will leak. This leakage will be seen even in the resting cells. And these potassium leak channels are more permeable to potassium than sodium. And this difference in permeability of ions, permeability is a key factor which determines resting membrane potential. And this, if you consider only movement of potassium from this potassium leak channels, this potassium will leak from inside the membrane to outside the membrane. Okay, they will leak from inside the membrane to the outside the membrane, and the ratio of potassium ions inside to outside, it is around 35:1. And with a formula, we can calculate a potential with the potassium diffusion. And if you substitute potassium value in that Nernst equation, we'll get a potential of potassium diffusion around minus 94 millivolts. And this this minus 94 millivolts is inside the fiber. This is the nerve fiber, and inside the nerve fiber we have minus 94 millivolts, which is caused due to diffusion of potassium from inside to outside. Inside to outside. Now we'll see second factor, that is contribution of sodium diffusion through the nerve membrane. What happens here? There is only slight permeability of sodium ions. There is only slight permeability of sodium ions, and this slight permeability of sodium ions will also cause potential, and these permeability is seen through potassium sodium leak channels, and the ratio of sodium ions inside to outside is 0.1. Normally inside the membrane we have less sodium, and outside the membrane we have more sodium, and the ratio is around 0.1. If you substitute this in a Nernst equation, we'll get a value around plus 61 millivolts. This is the diffusion, this is the potential which is caused due to sodium diffusion. Now we have two potential, one is with the potassium and another one is with the sodium. Now we have to have a summated potential. This summated potential will get through an equation called as Goldman equation. This summated potential from sodium and potassium, we have to substitute in the Goldman equation, and we'll get a summated potential around minus 86 millivolts. And this minus 86 millivolts is nearer to potassium potential, which is around minus 94 millivolts. Okay. Next contribution is through sodium potassium pump. What is the function of sodium potassium pump? It will pump 3 sodium outside. This is 3 sodium outside and 2 potassium inside. So with this, there is pumping of more sodium to outside than potassium ions to the inside. This causes continual loss of positive charges from inside the membrane, and they will create an additional degree of negativity. How much negativity? We'll get around minus 4 millivolts, and we have to substitute with the we have to combine with the summated potential. 86 millivolts plus minus 4 millivolts, we'll get around minus 90 millivolts of resting membrane potential. Resting membrane potential of a nerve fiber in a resting stage. So the resting membrane potential of a nerve fiber is around minus 90 millivolts. Now we'll see the action potential. Now we have seen resting membrane potential. Now we'll see the action potential. Whenever there is a stimulus, and this stimulus will cause action potential, and nerve signals are transmitted by action potential. To conduct a nerve signal, action potential moves along the nerve fiber until it comes to the fiber end. Whenever an action potential is generated, it will travel along the nerve fiber until the fiber end. So there are stages in the action potential. We'll see the stages separately. First is resting stage. So what is the resting stage? It is the resting membrane potential before action potential begins. This is minus 90 millivolts. Next is depolarization stage. What happens in the depolarization stage? Whenever there is a stimulus and the depolarization stage, the membrane suddenly becomes permeable to sodium ions. How they are permeable into the membrane? By channels called as sodium channels. Whenever there is a stimulus, these sodium channels will go into an active state, that is open state, and this sodium will be permeable through this sodium channels inside the membrane. There will be an opening of sodium channels which allowing tremendous number of sodium ions to diffuse to the interior of the axon. And this minus 90 millivolts is immediately neutralized by the inflowing positive charged sodium ions. That means this minus 90 millivolts will become minus 70, minus 60, minus 50, like that. this potential will move from towards a more positive side. So that means it causes potential rising rapidly in the positive direction. Minus 90, minus 70, minus 60, minus 50, like that it will move towards the positive side. That is called as depolarization. Depolarization. That is called as depolarization. In a central nervous system, we have large nerve fibers and a small nerve fibers. What happens in the large nerve fibers? The great excess of positive sodium ions moving inside causes the membrane to overshoot the membrane potential to overshoot beyond the zero level. We'll see that. And what happens in the small nerve fibers? They merely approach zero level. That means they does not overshoot. They will does not overshoot. Next is repolarization. Repolarization stage. After the membrane is highly permeable to sodium ions, within a few 10,000 seconds, what will happen? Within few 10,000 seconds after the membrane becomes highly permeable to sodium ions, this sodium channels will rapidly enter into inactive state, where there won't be any permeability of sodium ions. Now, in repolarization stage, potassium channels will open to a greater extent than normal stage, and causes rapid diffusion of potassium ions to the exterior. And this movement of potassium ions from interior to the exterior causes repolarization. That is, the potential will move towards the more negative side. Potential will move more towards the negative side. and opening of voltage gated potassium channels is slower and more prolonged than sodium channels. This slower return of potassium channels to closed state will cause after hyperpolarization. After hyperpolarization. That means the potential will move from minus 90 to minus 95, 96, like that. From minus 90 it will overshoot downside to minus 95 millivolts. This is called as an after hyperpolarization, and after hyperpolarization they will come back to resting membrane potential. Resting membrane potential. And the inactivated sodium channels will not open until the membrane potential return to or near the original resting membrane potential. Okay, sodium channels will go into the inactivated state. Then with that inactivated state they won't open. If you send a signal also, they won't, this sodium channels will not open until the membrane potential returns or it is nearer to the resting membrane potential. That means without repolarization the nerve fiber cannot be excited. We'll see a graph. This is a graph. Here is the time, 0.1, 0.2 and 0.3. These are milliseconds. Here we have potential. This is minus 90. This is minus 55. This is 0. Okay, the resting membrane potential is minus 90. Slowly, whenever there is a stimulus, this from minus 90 to minus 55, there will be a rise in the potential. This minus 55 to minus 90 is a threshold. And there will be a rising phase. And in a large nerve fibers, this rising phase will overshoot the above 0 level. And this is due to opening of this rising phase is due to opening of sodium channels. This is sodium channels, opening of sodium channels. This is a rising phase. This is an overshoot and a peak. Then later on, this potassium channels will open slowly and prolonged so that there is a downshooting of potential towards minus 95, like that. This is called as after polarization, after hyperpolarization, and again it come back to minus 90 millivolts, minus 90 millivolts. Okay, this is overshoot, this is above 0, this is a rising phase, this is a rising phase, this is repolarization. And this is threshold, this is threshold, minus 90 to minus 55 is the threshold. After it reaches the threshold, then there is a rapid rise of the graph due to opening of sodium channels. This is after hyperpolarization. This is how action potential will occur in a neuron. Thank you.